Hi, this is PC and you're watching Artificial Words. This episode is about quantum advantage. So if you don't know what's quantum computing, I refer you to my previous video where I actually explain what's quantum computing in easy words and where we are exactly. So as you might recall, we're in the NISQ devices era, which means noisy intermediate scale quantum. And that means we're not quite there yet in terms of development. We're probably like 60s, 70s compared to classical computing. But the whole idea of quantum advantage, that is practical demonstration that quantum computers are working faster than classical computers, is still in a play, meaning that we have already demonstrated that theoretically, and the whole idea right now is to show it and implement it on actual quantum computers. There's a lot of hype around that. You probably heard about how quantum computers will break all the passwords or like it's not safe, but we're still like dozens of years away from that. Where we are at right now is trying to find a niche problems which can give you much speed up on quantum computers. Rigetti put a $1 million prize for the first team to do that, and there are a lot of announcements similar to that, like Google trying to show quantum advantage, IBM, Microsoft working on that. There are a couple of companies who are like 1QBit, Zapata, who are also trying to work on the software part with regard to NISQ devices. And the whole idea of what we do at Bohr Technology, so this is my quantum computing venture, is trying also to show quantum advantage by basically looking at two kinds of problems. First of all, the problems which scale quickly and which are very hard hence for classical computers. This includes problems like traveling salesman problem and an NP-hard problem. On the other hand, problems where you have data sets which are sparse, meaning you have a lot of gaps in your data. You don't know, for example, those problems are in predictive maintenance when you're trying to figure out when a given device will break down. So for example, you have a turbine and it breaks down every 7 years, but you don't know when exactly. But when it breaks down, it's actually a huge cost for you to repair it. So you're trying to predict when it will probably break down and service it before that so that you cut the losses. And it's very hard to do because for classical machine learning, you have too few data to start with. So you're trying to figure out new ways, and quantum computing is one of the answers. So those two conditions, having sparse data and having problems that are scaling very quickly, are two conditions that of a problem that might give you a quantum advantage. And we're currently looking into that. If you want to know more about quantum advantage or quantum computing, I'll refer you to my Medium articles and leave a comment. How do you like it? What would you like to hear about more? I try to cover that in a text and in the video. Thanks.